Hello, this is T-Chapman500, and today I'm going to be showing you how the Serial Peripheral Interface, or SPI, works. So the basic setup for SPI is to have one master and multiple slaves. Now there are two basic configurations available for these slaves. One is like this, where each slave has its own slave select line, and the other is like this, called daisy chaining, where the output of one slave goes into the input of the next slave, and the output of the last slave goes to the input of the master. So the slave select lines are active low. That means if you put a 0 on the line, then that slave is selected. Now in the case of daisy chaining, we have all the slaves selected or deselected at once. Now let's take a look at the SPI master, of which there can only be one on the bus at a time. So we have a number of signals. We have 3 signals here, one for input into a shift register, the other 2 for outputs, and then we have 4 more signals here, one for each supported slave device. And this is implemented via a 2-bit address going into a demultiplexer. And of course we invert the output of the demultiplexer because the slave selects are active low. The enable line from the master comes from the control unit or some other device on the master. The master also generates the clock signal for the slaves and also generates its own clock signal. And we also have a few other signals to reset the register, to write to the register via the data bus, to read from the register via the data bus. And of course, this is how we interact with the slave devices on the bus. Now for each SPI slave, we again have a shift register. And one thing you might have noticed is that the shift registers sort of loop around. So if I were to go here, take a couple of shift registers, they loop around like this. So if this is the master, this is the slave, each clock cycle that the master generates, the data gets one step closer to actually being swapped. So the master and the slave swap data. Anyways, back to the slave. So we have the slave select, which when high drives the output into what's called high impedance or high Z, and that's how we are able to get multiple slaves on the same SPI bus. And again, we have a few extra signals that are generated by the control unit or other device on the slave, so that we can write to the register and read from the register. Now of course, this doesn't take into account other things such as generating an interrupt service request when this line goes low, but that is easy to implement outside the circuit. And the way I have these blocks set up is everything that can be accessed via the SPI bus goes right in between the slave and the master, with the slave on the right and the master on the left. Everything that cannot be accessed via the SPI bus is on the left, except for the reset signal, which is on the bottom. And for the SPI slaves, what cannot be accessed through the bus is on the right, except for the resets, which are on the bottom. Now the reason I've made these components is so that I can make a 16-bit microcontroller inside Logisim that I can program via the SPI, because I want this microcontroller, unlike the demo CPU, to be buildable through an FPGA or something like that. And I want a convenient way to get this thing programmed through something external to the microcontroller, and SPI would be the perfect candidate. So look for that 16-bit microcontroller in a future video, hopefully soon. And I'm going to attach an SPI slave and an SPI master as options for input and output interfaces. So that's how SPI works. I hope you enjoyed the video. Please leave a like if you did. Don't forget to subscribe for more, and check out the gaming channel for gaming related items. If you want to support this channel, you can do so via Patreon, PayPal, or Subscribestar. Links are in the description. This is T Chapman 500 signing off.